you have not got some pencil and paper, this would be a good time to grab some. We are going to take notes today. We're going to work sample problems. Oh, which reminds me, I turned my camera on there. Where's my extra work? We're gonna do sample problems. We're gonna take notes, and of course, any notes you have, you can use on assignments. You can use on tests. You can use on any of my semester final, anything that you're doing in my class. You could always use your notes on. Always, always. All right, getting my notes ready. Get my paper here. I've got to get a light. Not my new room. The lighting's kind of weird, so it's got a big shadow on my paperwork here. But we will do the best we can this week. Hopefully, you can still see it okay, and I will get some extra lighting in here as soon as I can find the keys in my cabinet. I think I locked them in this cabinet at the end of last year, and I don't have my keys for it. I don't know what happened to them. All right, set pretty good there. I think that'll work. Is that in focus? It gets as good as it gets. All right. I've got my notes ready to go. Hopefully, you got your notes ready to go. Got a few folks need to get their cameras on. Otherwise, I think we're in pretty good shape. Okay. Yes. Look at everybody here. Just missing like 2 people now. So, or just 1 person now. Okay. Good stuff. All right. Let me get the right screen up here, and we will get started with our first lesson in Algebra 3. And we're going to start with a lot of this is reviewing stuff that we should already know, but we've had a summer, and of course our mind went way off on summer stuff and away from school stuff. So a lot of this is going to be review early on, which is great. Week 2, domain, range, and function notation. All right. So, and you've talked about domain range for years in your math classes. Function notation you've seen before, but we're going to kind of do a review lesson this week. All right. Okay, today's roadmap. Here's what we're doing. We're going to talk about reading graphs. Look at domain and range on a graph. We're going to use a function notation like f of 3 means an output, not multiplication. There. We're going to talk about finding restrictions on different equations, denominators, square roots, cube roots, fourth roots, then create domain restrictions. And then we're going to have some practice stuff here. So our learning targets, we're going to find the domain and range from a graph, which is an easier way to find the domain and range than with an equation. We're going to find it algebraically also, and we'll interpret and use function notation. And then we'll justify why values are included or excluded, because often we have to exclude numbers from our domain. All right. Answer this in the chat. Rewrite x is greater than or equal to -2 in interval notation. Let's just see what you remember. We're just starting off. I'm gonna start my notes. I'll switch over to that. I say it's really dark. I gotta get some lighting on this or something. X is greater or equal to -2. How do we write that in interval notation? If you need a reminder, interval notation works like this. Oh, wait a minute. That's a greater than or equal to. So let me get this eraser. We're going to talk about this right off the bat. This side, I'm going to use a square bracket. Square bracket on that side right there. Now we'll see if you remember why I used a square bracket. Are you remembering yet? Is this coming back to you? Interval notation. So if x is greater than or equal to -2, that means the lower end of our x's, our domain, will be -2. And we put a square bracket because it includes -2. There's an equals to, greater than or equal to. So this means we need a square bracket. What's the upper end of our domain? Well, there's no limit, so it goes to infinity. Infinity, we always use the parentheses. Yep, Nancy had that infinity. We use parentheses because we can't. If I ask you what's the biggest number, well, it's infinity. There's not a biggest number, so we don't include infinity because we can't tell you the end. We can tell you the smallest number. It's -2, and it's included. We can't tell you the base. So infinity always uses brackets. Negative infinity always uses parentheses. Parentheses anytime on that, but on a number, it could be a parentheses or could end up the square bracket, just depending on whether or not it's included. So there's the first one. Let's see, do I have that? There it is. -2 with a bracket to infinity. All right, let's put this next one through that. All right, this one I'm going to let you put in the chat. Coordinates. If we're talking about like a point on the graph, name the ordered pair for a point that is 3 units left and 4 units up. Now, left of what? Up from the origin. Like if it's on a graph, from the origin, what is the coordinates for the ordered pair that's 3 units left and 4 units up? All right, I got it written in my notes. You guys got -3, 4, -3, 4. Perfect. Perfect. I drew a little illustration on mine just to show, it went left first and then it went up. So I know the X would be a negative and the Y would be a positive. So it was -3, 4. I just drew a little illustrations. So I was keeping that straight. I knew what I was doing. And it is -3, 4. Great job. Great job. All right. Why? Let's see. What value makes 1 over x minus 5 undefined? Oh. So a lot of times with our domain, it can be all real numbers, right? -infinity to infinity. But with this equation, there is a value to where you can't graph this one point because it's undefined at that point. Liliana's got an answer out there. Let's see, 1 over x minus 5. Okay, we can talk about that. 1 over x minus 5. Since the denominator has the variable x minus 5, we know that we cannot have 1 over 0. We can't have anything over 0. We can't have 0 in the denominator because that means take what's on top and divide it by what's on bottom. And we cannot divide by 0. That has no answer. It's undefined. There's no value when you try to divide by 0. That's when the world explodes. You got dogs and cats living together in sand. It's great. Just don't try it. Don't divide by 0. So if x minus 5 equals 0, then we've got a problem because it's 1 divided by 0. So x minus 5 cannot be 0. So when would it be? Let's solve. Add 5 to each side. So x cannot equal 5 because 5 minus 5 would be 0. That's how you solve that. Just take whatever is on the denominator, set it equal to 0, and solve. And when we do that, Liliana nailed it. She's on top of this. She remembers all of her earlier math classes, x equals 5. All right, so that's our little warm up just to kind of see what's coming up. Let's talk about domain and range. Inputs and outputs tell different stories. The domain, the range, all this good stuff. So when we look at the graph and we say, okay, what is the domain? It's all the possible inputs, right? So on a graph, we look at all of the x values that are covered by this function, the x values. So we can see down at the bottom, it's got the domain projection. It's got this orange line down here that shows from the smallest x, which is right here, all the way to the largest x that shows on that graph. That orange bar shows us this is the range of x's that are graphed above. Now the y's go up and down, but the x's, that's the smallest x right there, and it keeps going, and this is the largest x. There's not an x larger than 5. And then the range, we'll look at the range. That's all the possible outputs. Like when we take -2 and put it into the equation, apparently it equals 1 point whatever that is. We can't see exactly, 1.4 maybe when x is -2. When x is -1, the y equals 3. That's the output you get. If we had the equation, you could substitute in -1 and get 3. But we can see on the graph that when x is 2, y is -1. That's the output. So all the y's start way down here, and the largest y is up here. And we have that twice. We have it over here, and we have it over here. But that is the largest value of the output for our range. So if we want the domain of this equation, of, whatever this equation is in this graph, the domain would be -4 is less than or equal to x, which is less than or equal to 5. And then the other way we can write that, if we write it in interval notation, we would do a bracket, right? -4, trying to write with a mouse, doesn't always work too well, comma, and it would go to 5. And that would also be a square bracket because we have equals to on both of those. -4 is less than or equal to x. So x is bigger than -4, and it's smaller than 5 or equal to. So that is our domain. If we look at the range, looking at the green up and down line, the range shows us that this goes as low as -2 and goes all the way up to 3. So we could write that as well in interval notation. -2 and then 3 with a bracket on those as well. So reminding us there, this little review on domain and range, looking at a graph, which is the easiest way to do it because we can see visibly that the smallest x is at -4. Doesn't go any, there's no x's down anywhere past -4. And the same thing with the y's, we can see the range for the y's. All right, let me clear that out of there. So let's talk about interval notation. Quick reference here. So the notation should match the graph or the restriction, whatever it is. So brackets, as I was doing on our notes, brackets, the end point is included. In fact, I'm going to write this in our notes because this is good information. If we have forgotten this, let's talk about brackets. So the end point is included. So we use brackets when end points included. So on a graph, we would use a solid circle on that end point, right? It's kind of dark. I got to get some lighting in here. That's what we do on a graph. We use a closed dot. And then this would mean in our equation, it's going to be like a greater than or equal. I mean, when on our domain, if we're writing it in the other notation, it means it has the equal sign under it. So we got, these are the cases for that. Divide that. So those are dividers and not part of anything. So that is with the brackets. The next thing we would have would be the parentheses. So let's add that to our notes. If we're using parentheses, the end points not included And on a graph, we would use an open circle, and this would be greater than or less than or greater than. Yeah. So that's what that looks like with the parentheses. Endpoints not included, so we use parentheses. If we're graphing it, we use a hollow circle to show that it goes right up to that point, but it does not include that point. If we use infinity, let's talk about infinity here. Infinity, sideways 8. Infinity always use parentheses. All right, so we would put parentheses -2, 4, something like that. Always use the parentheses. And oh, there's one other thing that we need sometimes when we do this. Okay, let's see. So I'm writing this on my notes. I'll see what I'm putting. Putting what you had on the screen there. Brackets endpoints are included. We graph it with a solid circle, and it's less than or equal to, greater or equal to. And then I said with the parentheses, the endpoint is not included. It graphs with a hollow circle. It uses the less than or greater than. Then I'm making a note about infinity. Infinity always uses parentheses, like, parentheses, negative infinity to 4. Yeah, here's everything I have written so far. This was the answer to the first one. How do you write this in interval notation? X is greater than or equal to -2, so I wrote it like this. This was a point that was 3 to the left and 4 up from the origin, so that was the point. This was what is restricted for this equation. X cannot equal 5 because that would make the denominator 0. That's all I've written on my notes. And then I've got these 3 points. And then the other thing we have is sometimes you may have, well, let's say there's a graph. And on the graph, we have something that goes from here to here. And then there's a gap. And then the rest of the graph is over here. Okay, so our graph has 2 different sections of graph, right? So in that case, we might need to say, goes from here to here, whatever those numbers are. I don't have the numbers. And you've got this part over here from here. And in the middle, you would put this big U. Union. Let me just make up some numbers here. Like this went from -4 to -1, and this went from 1 to 6. Just filling in some numbers that could be. Union. It means and. So this is saying that when you put this union on here, this is the domain and this is the domain. Right? Because there's x's over here, but in between there, between -1 and 1, there's no x's included. That's not part of the domain. It's not part of this equation. It's not part of the graph. So we say, here's the left part and here's the right part. And it could be more than 2 parts. Maybe there's another piece that are, so you could have as many as you need to be able to tell where all the x's are for that. But we use that union. So that's the join separated intervals. So as it says on our slideshow right there. So let's put some other examples on our PowerPoint here. Uh, Brackets and parentheses. X is greater. That was the first example we had on the first page. X is greater than or equal to -2. We had to use brackets on the -2 because it was included because of the equals, and we had to use the parentheses on infinity. So that's kind of an example of a couple of these right off, right? So we got that example. Let's see what other example I got here. Oh, if x is less than 5. So in that case, we do have the infinity right there. So we have the parentheses on the negative infinity. And the 5 is not included because there is not, right there is not an equals. So this one's all parentheses, all parentheses. What if we have, oh, we have this case. Maybe it's one of those fractions where the x is on the bottom. And we figured out that x cannot be 3. So we can write that this way: negative infinity all the way to 3, not including 3. Notice that not including 3, and everything larger than 3. So that basically says everything but 3, right? Because negative infinity all the way to 3, and anything 3 and bigger, just not 3, because we have the parentheses on the 3. So that's a good example for that. Let's see, here's this one. -4 is less than or equals to, we got an equals under that one. This one does not have an equal. So we use a bracket on the -4 and a parentheses on the 5. Okay, so -4 less than or equal to x, less than 5. That means it goes from -4 to 5, including the -4. So if you want those examples in your notes, that's great. You know, if you need them or don't need them, maybe you got enough written on this other point to understand it. You take the notes you need to understand, but I think that makes it pretty clear on those. You can add examples. All right. Let's look at a graph. Reading the domain and range from the graph. Find the domain and range and explain how the end points affect your notation, right? So we need an answer for that. So in the chat, see if you can put what the domain and range is. I'll give you a chance to look at it. Let me give you a minute to look. Let you decide how that works. Then we're gonna watch a short video that talks about this as well. Being able to find the domain and range. In fact, why don't we do that first? Let's watch this video. We'll put this video up here. It is Khan Academy. They got some good videos there. So he's going to talk about finding the domain and range of functions. So let me change this where you can hear him talk, because the way I have it shared, you won't hear it. Okay, we're going to watch this 3-minute video, and then we'll come back to what we were doing.
All right, so let's do a couple of examples of trying to figure out the domain and range of a
That's
function
better.
based on a graph. So here we have the graph of y is equal to the absolute value of x. So pause this video and try to figure out the domain and range. All right, so let's start with the domain. And just as a reminder, this is the set of all of the x values that I can input into this function and get a valid output, or the set of all the x values for which this function is defined. Well, I can put any real number for x here and take the absolute value there. So I could say all real numbers. If I wanted to do it as an interval, I could write something like this. I could go from -infinity all the way to +infinity. Any of this would imply that, look, I could put any x in here. Now the range is a different matter. You can't get out all real numbers from here. You can see that you can go as low as 0, because the absolute value of 0 is 0. But everything else is going to be non-negative. So you could really think about this as all non-negative real numbers. All non-negative real numbers. Or if you wanted to write it like this, you could say, all right, we could include 0. So we could start at 0, and you can go up to positive infinity. And you can never go up to positive infinity. It's unreachable. So that's why we don't include it in the set there. And that's why we just have a parentheses. Now let's do another example. Let me turn that one off. So here we have the function y is equal to 1 over x. Pause the video again, try to figure out the domain and range. So the domain, what are all of the x values that I can input here? Well, 1 over x is defined for all x's as long as x does not equal 0. So I could say all real numbers x where x does not equal 0. I could do it in the interval like I just did, where I could say I could go from negative infinity up to 0 and union or add to that the set going from 0 to infinity. I can't include 0 here. So either of those would work. Now what about the range? What are all the possible outputs I could get out of this function? All the possible values for y, at least the way that it's defined there. Well, we're going to have a similar situation. Y can take on any value, except it can never quite be equal to 0. As x gets really, really positive or really, really negative, y approaches 0, but it never quite gets there. So it's actually going to be the same thing. So domain is also, well, I could do the same thing. You could go anywhere from negative infinity to 0. The range is the same thing, I should say. Union, you could go from 0 to positive infinity. You could also say all real numbers where y, or where f of x, does not equal 0.
All right, so that was a good review on using graphs to find our domain and range. So let me switch back to our question that we had before we switched that video. So in the chat, what is the domain? Let's just do the domain first. We'll do the range after that, but just the domain at this time. And you can put it in interval notation, or you can type it out like he did, all real numbers except, and that kind of thing. But this isn't an all real numbers one, so this is easy just to put it in interval notation. All right, I'm seeing brackets and parentheses. That's good because we have a solid circle on one end. We have an open circle on the other end. So anytime you do domain and range, make sure you're using parentheses or brackets, whichever is appropriate. But I'm seeing -4 to 5. So we can certainly see that -4 is the smallest x. There's nothing to the left of that, and there's nothing to the right of 5. This is a solid circle, which means it does include -4. This is a hollow circle, which means it does not include the 5, but it does include 4.9999999. All right, it includes everything except 5 up to that level. What about the range? All right, good job on that. Good job. Now, what is the range? So again, we've got the solid circle down here, and that is the lowest point. The graph does not go below that. So that is the value -2. The graph does not get any higher than this. That's the absolute highest point. Again, it is not included. So you've got it. Good job. So our domain, -4 to 5, with the -4 having a bracket, the 5 having parentheses. Our range is the -2, which is included, and the 4 is not. So closed dot, remember, includes. So we use the bracket. The open dot, not included. We use the parentheses. All right, let's switch a little bit. Oh, but while we're still talking domain and range, let me go ahead and show this other video on using equations for domain and range, because I don't want to skip on without showing that as well. Back up a little.
Determine the domain and range of the function f of x is equal to 3x squared plus 6x minus 2. So the domain of the function is what is the set of all of the valid inputs or all of the valid x values for this function. And I can take any real number, square it, multiply it by 3, then add 6 times that real number, and then subtract 2 from it. So essentially any number, if we're talking about reals when we talk about any number. So the domain, the set of valid inputs, the set of inputs over which this function is defined, is all real numbers. So the domain here is all real numbers. All real numbers. And for those of you who might say, well, aren't all numbers real? You may or may not know that there is a class of numbers that are a little bit bizarre when you first learn them, called imaginary numbers and complex numbers. But I won't go into that right now. But most of the traditional numbers that you know of, they are part of the set of real numbers. It's pretty much everything but complex numbers. So you take any real number and you put it here, you can square it, multiply it 3, then add 6 times it and subtract 2. Now the range, at least the way we've been thinking about it in this series of videos, the range is the set of possible outputs of this function. Or if we set y equals f of x on a graph, it's a set of all of the possible y values. And to get a flavor for this, I'm going to try to graph this function right over here. And if you're familiar with quadratics, and that's what this function is right over here, it is a quadratic, you might already know that it has a parabolic shape. And so its shape might look something like this. And actually this one will look like this. It's upward opening, but other parabolas have shapes like that. And you see when a parabola has a shape like this, it won't take on any values below its vertex when it's upward opening, and it won't take on any values above its vertex when it is downward opening. So let's see if we can graph this and maybe get a sense of its vertex. There are ways to calculate the vertex exactly, but let's see how we can think about this problem. So I'm going to try some x and y values. There's other ways to directly compute the vertex. Negative b over 2a is the formula for it. It comes straight out of the quadratic formula, which you get from completing the square. But let's try some x values, and then let's see what f of x is equal to. So let's try, the values we've been trying in the last few videos. What happens when x is equal to negative 2? Then f of x is 3 times negative 2 squared, which is 4, plus 6 times negative 2, which is 6 times negative 2, so it's minus 12 minus 2. So this is 12 minus 12 minus 2, so it's equal to negative 2. Now what happens when x is equal to negative 1? So this is going to be 3 times negative 1 squared, which is just 1, minus, or I should say plus 6 times negative 1, which is minus 6, and then minus 2. And then minus 2. So this is 3 minus 6 is negative 3 minus 2 is equal to negative 5. And that actually is the vertex. And you know the formula for the vertex, once again, is negative b over 2a. So negative b, that's the coefficient on this term right over here. It's negative 6 over 2 times this one right over here. 2 times 3. 2 times 3, this is equal to negative 1. So that is the vertex, but let's just keep on going right over here. So what happens when x is equal to 0? These first two terms are 0. You're just left with a negative 2. When x is equal to positive 1, and this is where you can see that this is the vertex. And you start seeing the symmetry. If you go 1 above the vertex, f of x is equal to negative 2. If you go 1 x value below the vertex, or below the x value of the vertex, f of x is equal to negative 2 again. But let's just keep going. We could try, let's do one more point over here. So we could try x is equal to 1. When x is equal to 1, you have 3 times 1 squared, which is 1. So 3 times 1 plus 6 times 1, which is just 6, minus 2. So this is 9 minus 2. It's equal to 7. And that, I think, is enough points to give us a scaffold of what this graph will look like, what the graph of the function would look like. So it would look something like this. Let me do my best to draw it. So this is x equals negative 2. Let me draw the whole axes. This is x is equal to negative 1. This is x is equal to, this is x is equal to 0. And then this is x is equal to 1 right over there. And then when x is equal to, we go from negative 2 all the way to positive, or we should go from negative 5 all the way to positive 7. So let's say this is negative 1, 2, 3, 4, 5. That's negative 5 over there on the y-axis. And then let me go to positive 7. 1, 2, 3, 4, 5, 6, 7. I could keep going. This is in the y, and we're going to set y equal to whatever our output of the function is. Y is equal to f of x, and this is 1 right here. So let's plot the points. You have the point -2, -2. When x is -2, this is the x-axis. When x is -2, y is -2. Y is -2, so that is that right over there. So that is the point -2, comma -2. Fair enough. Then we have this point that we have in this pink or purplish color. When x is -1, f of x is -5. When x is -1, f of x is -5. And we already said that this is the vertex, and you'll see the symmetry around it in a second. So this is the point -1, -5. And then we have the point 0, -2. 0, -2. When x is 0, y is -2, or f of x is -2, or f of 0 is -2. So this is the point 0, -2. And then finally, when x is equal to 1, f of 1 is 7. F of 1 is 7. So that's right there is the point 1, comma 7. And it gives us a scaffold for what this parabola, what this curve will look like. So I'll try my best to draw it respectably. So it would look something like that, and keep on going in that direction, keep on going in that direction. But I think you see the symmetry around the vertex. That if you were to put a line right over here, the two sides are kind of the mirror images of each other. There, you can flip them over, and that's how we know it's the vertex. And that's how we also know, because this is an upward opening parabola. I mean, there are formulas for vertex, and there are multiple ways of calculating it. But since it's an upward opening parabola, the vertex is going to be the minimum point. This is the minimum value that the parabola will take on. So going back to the original question, this is all for trying to figure out the range, the set of y values, the set of outputs that this function can generate. You see that the function, it can get as low as -5. It got all the way down to -5 right at the vertex. But as you go to the right, as x values increase to the right or decrease to the left, then the parabola goes upwards. So the parabola can never give you values. F of x is never going to be less than -5. So our domain, but it can take on all the values. It can keep on increasing forever as x gets larger, x gets smaller away from the vertex. So our range here, so we already said the domain is all real numbers. Our range, the possible y values, is all real numbers, greater than or equal to -5. It can take on the value of any real number greater than or equal to -5, nothing less than -5.
Okay, that had a lot of information. He was trying to figure out domain and range from a quadratic equation, and see where he figured it out is he ended up graphing it by hand, creating a table, XY table, graphing it. And so graphing is really the very easiest way to figure out the domain and range for any equation, which just kind of makes sense because it's right there visible where you can see it. So, okay, let's go. Our next slide, function notation. Now, this is very important to understand this. I know you've had it in multiple classes, so this is probably really basic for you. But if it's not, if you have forgotten function notation, then this is a good review for you. So let's talk about. We have this graph. F of 3, if we see f of 3, that means that is the output when x equals 3. When you see that 3 in there, that means that's the x value. And what is the y when the x is 3? Well, in this graph, we can see on a graph, it's 0. Because the x is 3, 1, 2, 3. The y is right there on the x-axis. So f of 3 equals 0 in this case. And when we read this, f of 3 is how it's pronounced. It's the value of f when x is 3. So when you see, the f of 3 right up here, you say f of 3. It is not mean multiply f times 3. That is not what it's talking about when you see f of 3. It is just saying there's a function named f, and the x that we're using is 3. That's what that means. And from the graph, we can see that f of 3 equals 0 on this. So function notation is something we're going to use in a lot of cases. And let's put an example in our notes of how function notation works with an equation. Because if we're going to talk about this, let's make sure we got something in our notes to refer to. So let's say we have an equation. F of x equals 2x squared minus 3x plus 4. Okay, so we have an equation. And we're going to find f of 3. Now, what we want to notice is this is where the x was in our equation, f of x. This is in function notation. This could also be y equals. But since this is in function notation, we need to use function notation up here. You can see that we removed the x and replaced it with a 3. So the way that works is we do the same thing on the rest of this. We remove the x and replace it with a 3. Every x becomes a 3. However many x's there are in your equation. Then we just simplify this. If we're inputting a number, our output should be a number. 2 times 3 squared. 2 times 3 squared is 9. So now we have 2 times 9. Minus 3 times 3. Minus 9. And then we have the plus 4. So this is 2 times 9 minus 9 plus 4, or 13 in this equation. 18 minus 9 is 9. 9 plus 4 is 13. So f of 3 equals 13. That's what our answer comes down to. F of 3 equals 13. But this is how function notation works. F of 3 means take the x out, substitute a 3 in. Take the x out, substitute a 3 in. Now, let me also note, because sometimes we'll see something like this. What if I had f of, and I'm using the same equation, Instead of f of 3, what if I do f of t? What's f of t? Same thing. I just take out the x and I put in the t. So it is 2t squared minus 3t plus 4. And that's it. I can't do any more because I don't have a value for x. There's nothing to simplify. So if it just gives you an expression, t, you just substitute that in. And we could also do f of like t plus 1 or something. And then we'd have a t plus 1 squared. We'd have to simplify that. And 3 times t plus 1, we'd have to put that in parentheses and distribute and all that kind of stuff. But whatever is in the parentheses is what you are supposed to substitute in for each value of x. I'll leave that there for a second if you're putting that in your notes, just so you have an example of how function notation works. So if we graph this equation, we put that on a graph, we would see that it goes through the point 3, 13. Because when we substitute in 3, it gets 13. So that would be one of the points that would be on the graph of that. Okay, let's go back to this. Finding domain algebraically. Most of the time, we're like, okay, let's just start out assuming that our domain and range is from negative infinity to infinity until we see something in the equation that tells us that cannot be. All right, so there are certain rules we can use to know whether the domain and range is all real numbers, negative infinity to infinity. So the first thing, in polynomials, that means x squared, x to the third, x to the fourth, all those things have more than one term. No denominators or even roots. No denominators, which means there's not a fraction in our polynomial. Nowhere does it have a denominator that has an x or anything in there. Or there's not a square root or a fourth root or a sixth root. So that's when it says even roots, it's talking about like a square root. Then the domain is all real numbers. If we do not see a denominator and we do not see a square root or a fourth root or a sixth root, the domain is all real numbers. Next rule. If there is a denominator, the denominator cannot equal zero. So set the denominator equal to zero, and then exclude those x values. Okay, so this is just give us some basic rules, just to know what the domain is. So if there's no denominators, no square roots, we know it's just all real numbers. If there is a denominator, solve the denominator equals zero, and those are not included in the domain, but it should be all the other numbers. The next rule is, what if there's a square root? Even even root, not odd ones. Odd ones is different. Even roots, square root, fourth root, sixth root, eighth root, even numbers. The radicand must be greater than or equal to zero. The number inside the square root is the radicand. That number must be zero or larger. If the root is in the denominator, maybe you have a fraction and the bottom of the fraction is a square root, then it cannot be equal to zero because it would be in the denominator. So this rule would also be in play. It can't equal zero. This, if it's not in a denominator, it can equal zero. It just can't be anything smaller than zero. And watch for combined restrictions. Like in this case, let's look at our rules up here. Uh, Obviously, the domain is not all real numbers because we have a denominator and we have a square root. So the first thing we see is the denominator cannot equal zero. So we have to solve for this equals to zero. So I'm going to put this in the notes as well so we can kind of go through this step by step on paper. It's easier to do this on paper than writing all this with a mouse. If I ever forget to switch the camera when I'm working this, please let me know. So, because I don't want to do all this and you not see what's going on. So we're having to look at the rules and figure out. The first thing we saw is it has a denominator. So x minus 1 cannot equal 0. So that would be solve this for x when x equals 1. So x cannot equal 1, right? So there's our first restriction to the domain. It can be everything else so far except for 1. Now we also have a square root. Now the square root is not in the denominator, so we got to use just the square root rule. The square root rule says that 2x plus 6 must be at least 0. Must be at least 0. It's got to be 0 or bigger because we can't have the square root of negative 4. There is no square root of negative 4. That's an imaginary number. It doesn't exist. It's not real. It exists as an imaginary number, I guess, but it's not a real number. And domains are dealing with real numbers. So, what number would be the smallest possible number? So, when this is equal to 0, let's go ahead and just set it equal to 0. Subtract 6. 6 is terrible. 2x is on this side, negative 6. Divide by 2. So, when x equals negative 3, this would be 0. And that's okay. It's okay for it to be 0, but we can't let it be smaller than 0. So in this case, would negative 2 be okay? Would negative 4 be okay? Which way do we need to go? Well, in this case, greater than or equal to, It's got to be at least -3. And we can test if we're not sure, because sometimes it could be the way 6 minus 2x would be different. If we substitute -2 in, 2 times -2 plus 6. All right, I'm just taking the 2x plus 6 and substituting a different number. 2 times -2 is -4 plus 6. Okay, that's a legal number. We can take the square root of 2. But what if we went the other direction and said 2 times -4 plus 6? 2 times -4 is -8 plus 6. We can't have a negative. So it's got to be numbers bigger than -3. Because when I went a smaller number, it gave me a negative. So the domain would be greater than or equal to -3. Can't be 1. So our domain, let's say, can be -3. All right, because we said that all the way to can't be 1. 1. -3 to 1. And so we put that union 1 to infinity. So it could really be anything bigger than -3 all the way to infinity, except we got to take out 1. So both of these, this was because the square root rule, this was because the denominator rule. So this is our answer in interval notation. We could have put all real numbers greater than -3 except x cannot equal to 1, but that's a lot of writing when we can just put an interval notation. But it's okay to write it the other way. All real numbers greater than or equal to -3 except x cannot equal 1. All right, do you see how we got that? Do you see how we use those rules? And if you want to write those rules down in your notes, the rule for polynomials, the rule for denominators, the rule for square roots, that would be very wise just because you'll have those to refer to in any test or thing. Uh, the rules tell us that the square root has to be greater than or equal to 0. So that's what we solved. And we found out that as long as x is -3 or larger. And the denominator rule tells us that x minus 1 cannot equal 0. And that led us to this domain where we said -3 to 1, union, and 1 to infinity. So finding the rule that helps you get there. Otherwise, we can graph it and look at the graph, but it may be confusing as well. Maybe it's easier just to look at it this way. What we'd see is we'd see an asymptote at 1 if we graph it. So why don't we go ahead and take a look at that? Here, I'm going to put this up on the screen just so we can look and see what it looks like if we put the same equation in the graph. So we have the square root 2x plus 6 outside parentheses divided by x minus 1. Okay, that is our equation. I can put a y equals, but it's going to show the same thing. So if we look at the graph, we've got to zoom out. We see that it goes all the way down to, and it does include -3. It does include -3, but it doesn't have anything smaller than that. Not a thing smaller than that. And as it gets larger, the x's, there's an asymptote there. See, it never touches, let me put this, x equals 1. It does not touch x equals 1 because that's where the denominator told us x cannot be 1. So when we do our domain, we include this part over here from -3 all the way to 1, not including 1, and then everything bigger than 1. is the other part of the graph. So that could be kind of confusing. Look at the graph trying to figure out how to write that. So it's also helpful just to have these rules that we can use and just figure it algebraically. All right. And you will have access to this PowerPoint. I'll put it in our Google Classroom if you need to come back and if you're trying to finish your notes and want to write any of this down, or if you if you have a printer, you can print off pages from this and use that as notes. I'm fine with that too. All right. Let's look at another one. Example 2. Use the restriction rule that matches the formula. We have 4x to the third minus 2x plus 1. What do our rules say? Well, our rules said if it's a polynomial, which this is a polynomial, if it has no denominators, no square roots, fourth roots, sixth roots, um, does this have a denominator? No, there's no fraction. Does this have a square root or a fourth root or a sixth root or any kind of root? No. So that tells us that the domain of this must be negative infinity to infinity. This graph will go forever both directions. Like seriously? Well, yeah. Let's just graph it. Let's just graph it to look and see. We're saying it goes forever. This is 4x to the third minus 2x plus 1. Oh, look, it's one of those. Got squigglies in the middle. It goes down really, really fast, but it keeps going left. Look, the farther we go, it's still going left, and it will go left all the way to negative infinity. It's just going to take a long time to get there. And in the same fashion, it is going right as we go up, very slowly to the right, but there's no limit, and it will continue forever. So the domain has no restrictions. It goes from negative infinity to infinity. And that's what our rules told us. There's no restrictions to that. Let's look at another one here. How about this one? What our rules say. Polynomials that don't have denominators or even roots. Oh, wait, this has a denominator. Okay, so we know there's a restriction. It's not negative infinity to infinity. Does it have a root? No, there's no roots at all. There's no even roots, no odd roots. There's no square roots, nothing like that. So we are only restricted by the denominator. So let's figure that out. So our equation, x plus s, I got it up here, x plus 5 over x squared minus 9. Okay, that's our equation, f of x equals. So we know that x squared minus 9 cannot be 0. X squared minus 9 cannot be 0. Well, what would make it 0? Add 9. So that means x squared equals 9. And if we have x squared, we take the square root of both sides. That's how we get to x. So this is just x equals, what is the square root of 9? Be careful there. What number multiplies by itself to be 9? 3. And negative 3. There are two restrictions. Because negative 3 squared is 9, minus 9 equals 0. Positive 3 squared is 9, minus 9 equals 0. So with this one, we can't have negative 3 or 3. So our domain is going to be negative infinity all the way to negative 3. You do it smallest to largest, always smallest to largest. And from negative 3 to 3, and 3 to infinity. This is basically all numbers from negative infinity to infinity, except for negative 3 and positive 3. That's this. Or you could say, if you wanted to, all real numbers except x cannot be -3 or 3. You can say either one of those. All real numbers except x cannot be -3 or 3, or from negative infinity to -3, -3 to 3, and 3 to infinity. That's what our rules told us. The rules said, okay, no square roots. I only have to look at the denominator to figure out what is not part of the domain. So the rules can help us make this a little easier trying to figure it out, especially if graphing it is hard to do. Some of these equations may be tricky to graph. So that tells us x cannot be -3 or 3. And there is that domain that we wrote in our notes. All right, I'm going to get one for you to do and put the domain in there. Use the rules. Here you go. Look at the three rules: polynomial, denominator, even roots. What is the domain? Write this in your notes. Work it out. I'll show the answers. So if you need to correct anything afterwards, put this down in your notes. Put it in the chat when you get an answer what the domain is. Actually, list the whole domain. Give those three rules in your notes, and it helps. What is the restriction? Once you figure out what the restriction is, you can calculate and put the domain in the chat. This one obviously does have a restriction. We have an even root. A square root is even. That's the root 2. 2 is an even number. All right, Camden's got an answer in there. Yeah, our keyboard doesn't have a little sideways 8 for infinity, so you can put INF if you want to. You don't have to type the whole world, the whole word. Camden's got an answer. Anyone else agree? Disagree? Got a different answer? Got the same answer? All right, lots of agreeing there. Other people come up with the same thing you came up with. That's good. Yes, you look at the root rule where it says whatever is underneath the square root, which is called the radicand has to be greater than or equal to 0. So that means x minus 4 has to be greater than or equal to 0, which is the case as long as x is 4 or larger. And it does include the 4. So good job of using the bracket, because the 4 is included because it can be 0. The square root of 0 is 0. It's a legal number. It just cannot be anything smaller than 0. So good job. If you got something different, go back and look and see what you did wrong. You should have taken x minus 4, set it equal to 0, greater than equal to 0. Solve for x. You just have to add 4 to both sides. So x is greater than equal to 4, and that's how you'd write the domain. All right, let's take another one here. Work this, put this in the chat. U of x equals 1 over the square root of x plus 2. So let me put that in my notes as well. I'm going to let you work it and put it in the chat before I show what I did. 1 over square root of x plus 2. This is affecting two of our rules. This has a denominator and it has an even root. It has a square root. So you have to kind of combine those two rules. and figure out what is the domain. Put your answer in the chat when you have that. I'll put my answer up in a minute or two or less. All right, Camden's got an answer. Get your answer before you check and see what Camden put, though. So you can see if your answer agrees. All right. Nancy's got a different answer. That's my work of yours first, because you may end up with a different number. Nope, Camden's amended her answer. Good, good, good. Yeah, don't forget that little negative can get us sometimes. X is greater than or equal to -2. Our square root rule says this has to be 0 or larger. But when you also see that it's a denominator, now it can't be 0. So it just has to be larger. X plus 2 has to be larger than 0 because it's in the denominator. Denominator says it can't be 0. Square root says it has to be 0 or larger. So when you combine them, it just has to be larger than 0. So solve that for X. So -2 would make it 0. So it has to be larger than that. And so we use the parentheses on both sides of our interval notation. Great job, great job. So there it is. X plus 2 is greater than 0, the domain -2 to infinity. Okay, let's look at this. Here's graph B. Find the domain and the range. Are the endpoints included? Group practice here. So we have a graph. So looking at the graph, I'm going to start talking my way through this. The domain and the range. I'm going to put up my answers here in just a moment and see if you got the same thing. Looking at the graph, the smallest x is at -3, the largest x is at 3. So I got from -3 to 3, and I used brackets. And then the range, Camden put 1 to 4. Nancy had the -3 to 3. It is included because you have this. Is 4 included? It does touch the point of 4. So we should be using brackets all around on that. Yeah, I put -3 to 3 and 1 to 4, all with brackets. All right, you guys getting the hang of this. This is good, good, good. How about this one? What's the domain of f of x equals the square root of x plus 5? We've done one like this. We know that this has to be at least 0. It can be 0 or larger. So the smallest number it can be, right? It could be -5, right? Because -5 plus 5 is 0. We can include that and go to infinity. It can be anything bigger. -5 to infinity. Perfect. Good job. Okay. Let's throw another practice on that there. How about, oh, look at that. Oh, there's going to be some work. I better write this one down. I wonder if I have room left on this paper. We're going to try and see. I think I might have enough room. Well, we have this equation. 2x minus 1. I write that down right? Yes. X squared plus x. So we know that there's no square root, so I don't have to pay attention to that. The polynomial rule does not apply because there is a denominator, so we have to go over to the denominator rule. The denominator rule says this cannot be 0. X squared plus x minus 6 cannot be 0. Anything else is fine. It could be a negative number, it could be a positive number, but it can't end up 0. So we have to figure out what would make this 0. This is a quadratic equation, which means we need to factor this. So the middle term is a 1 plus 1. The last term is negative 6. So if I want to find plus 1 and negative 6, I need two numbers that multiply together to be negative 6 and add together to be 1. So what multiplies together? Excuse me, 1 and negative 6. That would multiply to be negative 6. Or negative 1 and positive 6. Or if I had 2 and negative 3, or negative 2 and positive 3. Any of these combinations of numbers multiplied together would give me negative 6. But I need to add together to be a positive 1. Add together. This would be negative 5 when I add those together. That'd be a positive 5. 2 plus a negative 3 is negative 1. Negative 2 plus 3 is 1. These add together to be 1, multiplied together to be 6. So this factors to x minus 2x plus 3. Just a little quick factoring. I know you've done a lot of factoring in the past. So if either of that equals 0, if these equal 0, if this is the same equation, this is just factored form, standard form. If it equals 0, this doesn't work. So that means if x minus 2 equals 0 or x plus 3 equals 0, so add 2, x cannot be 2 minus 3, x cannot be negative 3. So our domain would be negative infinity to negative 3 and negative 3 to 2 and running out of this room here 2 to infinity. Negative infinity to 3, 3 to 2, and 2 to negative infinity. And we don't include the negative 3 or the 2 because it cannot be those two numbers. But it's basically negative infinity to infinity except for 2 and negative 3. And we put the negative 3 first because we always do smallest to largest. Negative 3, 2. But with this, we just have to factor it and find out what x is. If we substitute 2 into this equation, it'll equal 0. If we substitute negative 3 in this equation, it'll equal 0. And either way makes this undefined because we cannot equal 0. And this one, this is just context. I don't want you to solve this because I haven't given you any value for m. This is you get in a taxi, and this is how they charge their fees, right? This is the equation they use. 25 plus 0.10 m. So m would be what? What does m stand for? If you think, what do you think of this? What's the taxi going to charge me? 25 plus 0.10 m. Put that in the chat. What would m be in this situation, in the context of this little word problem? What would the m stand for? Any guesses? Minutes? So for however many minutes you're in a taxi? Not quite. Not quite. I like your thinking though. Miles? Most likely it would be miles because if they take you a long ways, they're going to charge you more. If they just take you a short distance, it charges you less. So that is miles. So given that, what would the domain be? What values of m make sense? Now, looking at the equation, it's a polynomial. It's just 25.1. We could say negative infinity to infinity. But that doesn't make sense when we put it into a word problem. That's when context comes in. Okay, in the context of things, it's not negative infinity to infinity. I'm not going to get in a taxi and say, take me infinity miles, right? Maybe. I mean, you could, there's really not an upper limit. You could drive 1,000 miles, 2,000 miles. But what values of M would we exclude? Think about that. Would there be any values that you would not include? If M equals miles and you're calling the taxi, thank you, Nancy, you're right on top of it. We would exclude the negative numbers. We don't call a taxi and say, I want to go -3 miles. How much is that going to cost me? Now, in the context of the problem, we have to exclude all. We can have 0 miles. We call the taxi. He shows up. We get in. Oh my gosh, I forgot. I'm not ready to go. But you got to pay them the $25 because they showed up and you got in the taxi. Zero and positive numbers are the only numbers we would include. Not because of one of those rules, because the rules that we looked at, there's no restriction, there's no denominator, there's no square roots. But the context of the problem. So if you're working a word problem, anytime you're working a word problem, do the math, right? Do. And then when you get your answer, before you put your answer down, go back and look at the question and see if your answer would work for that. And let me think of it like this way. Maybe you have something like uh, Paula is throwing a party and she knows that each guest can drink 2 sodas. So she buys sodas, right? She now has at her house 15 sodas. How many people can she invite to the party based on the amount of soda she has? Right? So do the math. You'll say, okay, she's got 15 cans of soda. She's going to plan on 2 cans for each person. So I look at it, I divide 15 by 2, 7.5. Okay, Paula can invite 7.5 people to her party. Does that make sense? Would you say Paula can invite 7.5 people to her party? No, because the context, 7.5 would be the mathematical answer, but the context says no, she can only invite 7 people. Because if a half a person shows up to her party, everyone's going to freak out and run away because nobody wants to see half a person laying there. So, yes, use context anytime there's a word problem. Work the math. The math says 7.5, but go back and look at the question. The question said, how many people can she invite to her party? Okay, so that would be 7 because of the context. I have to change my answer to just be 7, not 7.5. So that's all I want you to think about on word problems. Work the math and then go back and read the question just to make sure your answer makes sense, or do you need to round it or something like that. So values of M make sense. If you worked something and come up with a negative number of miles, you'd say, oh, wait a minute, that doesn't work. Oh, I paid $20, which means I drove negative 50 miles. No, 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 no. Something must be wrong. I didn't do something right. All right. We are almost out of time. I had some more problems if we needed them. Uh, this is just some more practice if we need to review as a class, but we're about out of time. So I'm going to show you the assignment and let you have the rest of this time to get started on that. Where am I at? Oh, yep. Okay. Here is our Google Classroom. If you go to the classwork tab, you may have already seen this, week 2 assignment. It is on formative. When you click on that, it'll take you to the formative website. You may need to log in with your school Google account, or it may already have you logged in if you've been there already this previously. Here's what the problems look like. Here's what our assignment looks like this week. Algebra 3, week 2 assignment. Find f of 4. We went over what f of 4 means, right? You go in here and f of x, but we're taking the x out and putting in the 4. So solve that. You should come up with just a number. When you take 2 times 4 squared minus 5 times 4 plus 3. It does have a hint, right? It does have a hint you can get. F of -1, G of 7, G of -9, H of 5. So there's several of those. Now we talk about domain. If H of x equals 1 over x minus 2, why is H of 2 undefined? What is the domain here? Put an interval notation. What is the domain here? What's the domain here? What's the domain here? And then finally, we got a graph at the end. What's the domain of this graph? What is the range of the graph? What's the domain of this graph and the range of this graph? So 15 problems, domain and range, and interval notation, substituting numbers in and just coming up to an answer. I try not to do anything that was like a trick question. I don't like trick questions necessarily, but there you go. That's what we got this week. 15 problems. If you have any problems or questions, I will be in class on Thursday. You do not have to be in class on Thursday since you are here today and nobody's grade is below 70% because we haven't had any grades yet. So I will be in class if you need help, but you're not required to come this week since you made it to class. So I will let you have the rest of this class time. If you want to work on this, advisory is today in about 15 minutes. So you got 15 minutes and 15 problems. You may or may not be able to get them all done. But if you get some of them done and leave it, you can save your work so you don't have to do them later. So, all right, guys, have a great week. I'll see you next Tuesday, if not before.